Hi, I'm Jeff Perry, the manager of the WEBENCH team at Texas Instruments. Today I'm going to talk to you about WEBENCH efficiency calculation and design optimization. WEBENCH consists of multiple different layers of design tools. Today we're going to be talking about the individual WEBENCH Power Designer tool, but there's also the WEBENCH Visualizer and WEBENCH Power Architect tools, which are covered in separate training sessions. To access WEBENCH, by the way, go to www.ti.com/WEBENCH. Okay, today we're going to talk about design optimization and efficiency calculations. To start out with, we have a schematic of a buck converter. The components in the buck converter include the input capacitor on the left, regulator with an integrated FET, an inductor, the catch diode, the output capacitor, and the feedback networks, and other peripheral components. Now, in order to calculate the power dissipation, the first thing we need to do is figure out the currents through the different nodes of the circuit. So in a switching regulator, when the MOSFET turns on, the current flows from the input through the MOSFET and through the inductor. Some of the ripple currents will be flowing through the input and output capacitors. With the switch off, the current is flowing through the catch diode and the inductor into the load. So it's important that we calculate the currents through these nodes first. We use conventional equations in WEBENCH to calculate these currents at these nodes. To calculate the efficiency, we'll first look here at a series of graphs that were produced in WEBENCH that show these different parameters versus the load current and the input voltage range. For example, in the upper left we have a plot of efficiency on the y-axis versus the load current on the x-axis. The different colors here are the different input voltages. Now, efficiency is calculated by simply taking the output power divided by the input power. The input power can be calculated simply by V out times I out plus the power dissipated. Now, in order to calculate the power dissipated, we'll go to each individual component in the schematic. Starting with the diode, we have the switch current times the forward voltage drop across the diode times 1 minus the duty cycle, because the current's only flowing through the diode when the switch is off. The input and output capacitors are simply the RMS current squared times the ESR of the capacitors. The power dissipation in the switch is a little more complicated. You have DC losses, which are, again, I squared R, in this case the R being the RDS on of the switch, times the duty cycle. The AC losses are proportional to the input voltage times the switch current times the rise and fall time of the switch divided by the switching period, which is 1 over the frequency. The switch also has quiescent current losses, which are proportional to V in. And last but not least, we have our inductor losses, which are again I squared R, with the R in this case being the DCR of the inductors. Now, there are other loss mechanisms that are taken into account that have to do with core losses for the inductor and other issues that I'm not going to cover on this slide. But these are the core loss mechanisms. Let's talk a little bit more about the AC losses in a FET. This is a diagram of how a FET would turn on, a MOSFET would turn on. The green here is the gate voltage. And you can see here with the switch off, there is no current flowing through the switch, and there is a voltage dropped across the switch. Now, as the gate voltage turns on to the threshold, current will start to flow through the switch, but at that same time you still have voltage across the switch. When the gate reaches the Miller threshold, Miller plateau I should say, the current is flowing and the voltage across the switch starts to drop. And then finally, when the voltage reaches its minimum across the switch and you have full current flowing, we are out of this AC loss regime. Same thing happens when the switch turns back off. There are losses during this transition time where you have both current and voltage flowing through the switch at one time. Now, in order to reduce these losses, you can change your switching frequency. There's a little schematic up here in the upper left diagram showing what happens when you increase your switching frequency. These rise and fall time areas of loss become a larger and larger percentage of your switching time period, and therefore the AC losses can really dominate each switching cycle, and you can get a very heavy power loss and low efficiency. But lowering your switching frequency reduces the percentage of time that these areas of loss are in the switching period. So one simple way to reduce loss mechanisms in a power supply, switching power supply design, is to reduce your switching frequency. You can also choose a FET with low RDS on. That reduces your DC losses. Another way to do this is also to choose a FET with low gate charge. That increases, or I should say reduces, your rise and fall times, and that will reduce those areas we just talked about. And then, as I just mentioned, you can also lower the switching frequency. But lowering the switching frequency also affects the inductor selection. We want to keep the inductor ripple current constant because we don't want to have too high of a peak switch current, and we also want to maintain our Vout ripple. Let's explain this in a little more detail. This is a diagram showing what's happening with the switch voltage. So as the switch turns on, the voltage on the left side of the inductor goes high, and then as the switch turns off, the voltage goes low. And so you have this voltage being changed across the inductor, and the inductor current will ramp up and down accordingly. Here's a blow-up of that, a little more detail. So the voltage applied in this case is the input voltage minus the output voltage, and the on time is proportional obviously to your switching frequency and your duty cycle. The fundamental inductor equation here says that the change in the current will be inversely proportional to your inductance times the voltage applied times the time that that's applied. So all the time that we're applying this input voltage, the inductor current is rising, and then it falls back down as that voltage is turned off. Okay, so let's take another look at what happens when we lower the frequency. Okay, so this diagram here is to scale, and it shows that if we decrease our frequency and maintain the same duty cycle, this on time is going to be longer, and therefore our inductor current is going to rise more. This peak-to-peak inductor current, though, we want to maintain at this low level because we want to maintain our Vout ripple, and we also want to not violate our peak switch current. So in order to bring that back down again, what we do is we increase the inductance, and that's because that's on the bottom in this equation. So increasing our inductance allows us to lower our switching frequency and still maintain the same peak-to-peak inductor ripple current. What effect does that have on the design itself? Well, an inductor basically has to get bigger. That's because to increase your inductance, you have to have more turns of wire, and often with more turns of wire, you're going to have higher resistance, so you need larger diameter wire to keep that resistance down. So you may go from a small inductor, shown here on the left, over to one that gets relatively huge if you drop down to switching frequencies of 100 kilohertz and below. So this is the basis of the WEBENCH design optimization. In WEBENCH, we have a simple knob control that lets you either prioritize small footprint, high efficiency, or low BOM cost. And this table tells how we do this. For small footprint, we set the frequency to the highest value that the part will allow. In our component selection, we choose components with small footprint and really don't care too much about the cost. This results in the smallest size designs but the lowest efficiency. For knob setting 2, for lowest BOM cost, we still maintain a high frequency, and that's because it turns out that high frequency, these smaller components, tend to be lower cost. And in our component selection algorithms, we also allocate more priority for low-cost components. This results in a design that is smaller and has cheaper components than other designs at the other knob settings. Knob setting 3 is a balanced approach, where we use a middle-of-the-road frequency. In this case, we look for parts that are in stock and are relatively low cost. As we go to knob setting 4, we lower the frequency even more. So now we're targeting higher efficiency, and we're looking for parts with low DCR, ESR, and forward voltage drops. And at knob setting 4, we're also still looking for low cost. So this results in higher efficiency, but still maintaining a reasonable low cost target. If you set the knob setting to 5, we use the lowest possible switching frequency for the part. We also prioritize the parasitic resistances at their highest weighting, so looking for very low DCRs, ESRs, and forward voltage drops. And at this point, we don't care too much about the cost. This gives you the highest efficiency, but also the largest parts, and it can also tend to be a little more costly. If you click on the Optimize page here in WEBENCH, you can see graphs of everything we just talked about. So on the left side, you're showing, on the x-axis of these graphs is the optimization setting for that knob. So optimization 1 being small footprint, optimization 5 being high efficiency. In this case, you see the power dissipation, and you can see it going down overall for the components as we go to these higher efficiency designs. You can see the green here is the switching frequency, and we're lowering that as we go to these higher optimization settings for high efficiency. This is a graph of the efficiency in green and the footprint in orange. And you can see that as we go to these higher knob settings for high efficiency, we are getting indeed an increase in efficiency from 75% all the way up to about 84%. But the footprint is also increasing, going from less than 400 square millimeters up to 1,400 square millimeters. Just a note about the footprint, that's basically the footprint of the components itself, not necessarily the footprint of the entire board layout at the end. And then over here on the right, we see a graph of the BOM cost. And you can see here that the BOM tends to be higher cost at the high efficiency settings and lower cost here in the middle and over on the knob setting of 2. So let's try a hands-on exercise here. We're going to use design requirements of 14 to 22 volts input, 3.3 output, 2 amps using an LM22670. And let's try to optimize the design for the different targets. Okay, here I've created a WEBENCH design. I went to ti.com/WEBENCH and used the WEBENCH panel on the right side of the page, and then I selected the LM22670 as our device. You can see over here the inputs are 14 to 22 in, 3.3 out at 2 amps. The default design here has a footprint of 454 millimeters, square millimeters I should say, a BOM cost of $3.40, and efficiency of 79%. Let's try to target a high efficiency design first. I clicked on the optimization knob, and WEBENCH went off and optimized this design. So now I see that my efficiency has gone from 79% up to 85%. My cost has increased a little bit though. I've gone from $3.40 to almost $5, and the footprint has gone from 454 square millimeters to over 1,100 square millimeters. Let's target small footprint next. Here's the small footprint design, and indeed the footprint has decreased quite a bit, just below 300 square millimeters, but the efficiency has now dropped to 75%. If I want to go to low cost, that's usually on either knob setting 2 or 3, so let's try 2 first. Now our cost is $3.30, and so that is indeed the lowest cost of the optimization settings. Let's take a look at the optimizer graphs over here. So I'm going to click on that screen. And what we see here is the graph of the power dissipation versus the optimization setting. And we can see here our efficiency is indeed climbing from around 76% up to 85% over those different optimizations. And so something in the middle here might be a footprint of 454 square millimeters and an efficiency of almost a little over 79%. You can see the cost here is lowest on knob setting 2 and climbs up here as you go to the higher efficiency designs. So overall you can see here that WEBENCH allows you to make fundamental trade-offs in the design that only you as a designer can make for your purposes. Okay, today we've covered the WEBENCH optimization, basically covered how the power supply efficiency was calculated, requires determination of the circuit's currents and power dissipation for key components using the fundamental equations. Efficiency can be improved by reducing the switching frequency, but this causes inductor and other components to be larger. There's a fundamental trade-off between efficiency and footprint in all power supply designs, and only you as a designer can make that decision. So the WEBENCH optimizer allows you to look at those different cases and quickly optimize your designs for any one of the high efficiency, small footprint, or low cost priorities. And overall, WEBENCH design tools will save you time. Thanks for your time, and I encourage you to try WEBENCH tools yourself at www.ti.com/webbench.